point as of now is the stress strain curve for structural steel. If I have to draw it for mild steel, it looks something like this. Okay. So if I have to use mild steel in reinforcement as well, the stress strain curve is going to look exactly the same, because we've seen that steel is a homogeneous material, and it shows the same, it more or less it shows the same stress strain curve. So if I look at the stress strain curve for mild steel that is used in concrete design, so what the code does is, instead of having this curve, what it does, it simplifies this curve to a mere triangle rectangle. So this is nothing but a simplification of the stress strain curve that we've seen in the past. So what we see here is the limits are still the same. This is the characteristic curve, or the curve, uh, the 5% the 5 percentile strain that we've seen. So that is this characteristic curve. This is a specified yield stress Fy. To obtain the design curve, what we do is we just divide the yield stress by our partial safety factor, which is 1.15 for steel, and then 1 upon 1.15 is 0.87, and therefore we get 0.87 Fy. So when we divide the characteristic curve by 1.15, we get what is our design curve. Okay, it is pretty straightforward for mild steel because it has a well-defined yield point. This point is something that is relatively known in mild steel. So now our design stress is 0.87 Fy, which is nothing but Fy upon partial safety factor, and corresponding to this, our strain is, we know that E is equal to stress upon strain, and hence the strain is stress upon E, which is 0.87 Fy upon Es. So this is the yield strain for mild steel. Pretty straightforward. When we go to high strength steels, when we go to HYSD bars, which have strengths like which have yield strengths like 415 megapascals, 500 megapascals, 550 megapascals. Please know that these are the commonly used steels in actual practice. Mild steel is very rarely used these days. Uh, I have had not got a chance to use mild steel anywhere. So in terms of applicability, I believe the curve that you see on the right is more applicable. So what happens in high strength steel? We've seen this in the past also, that they do not have a well-defined yield point. So if I have to draw the curve for HYSD bars, or perhaps I'll just draw the curve here itself so that you get a feel of how they compare with each other. So this curve would be something like this, in which there is no well-defined yield point as we have in case of mild steel. Okay, but one thing that we've seen before, and just to reiterate it, that these two curves sort of overlap in the linear elastic region, and then the high strength steel curve goes higher because it has higher yield strength. So now we need to set a certain rule for defining our yield stress, for defining our yield point. Here it's quite clear, here it's not that clear. So what we do is, at a strain of 0.002, we draw a line that is parallel to the elastic portion of the curve. And wherever the line hits the curve, we say that this is our yield stress, and the corresponding strain is our yield strain. Okay, so we'll get into why, and why this particular number, and how it is done. But first, just understand the process. On the left side, it is well defined, easy. On the right side, the yield point is not a well defined point. So we have to set a certain criteria for defining a yield point. Okay, to do so, what we do is we just draw a line that is parallel to the linear elastic portion, and wherever the line cuts the design curve, that particular strain is our yield strength, and that particular stress is our yield stress. Okay. Now here we did not offset anything and draw a parallel line. We already knew what the point was. The yield strain here is 0.87 Fy upon Es, which is the Young's modulus of elasticity for steel. Here we'll have an additional component of 0.002. So the strain here is 0.002 plus the stress upon modulus of elasticity, which is 0.87 Fy upon Es. Okay, so this is a very important term to remember. We are going to use it now and then in flexure, a very important term. Epsilon y is equal to 0.002 plus 0.87 Fy by Es. This is a strain in steel when it yields. Okay. Now the question is, why 0.002? I mean, why at all is there a need to offset it? Okay. So since there is not a well-defined yield point, we assume that if the load, if because of the load, there's a certain permanent residual strain that is left in the material, we can say that, okay, the material has yielded. Okay. Now, what do I mean by a permanent residual strain? When we start loading, say, so when we start loading, we will get a curve like this. As we continue loading, we'll sort of deviate from our linear behavior. We'll deviate from Hooke's law, and we'll get into inelastic region, and then further we'll get into plastic region. Okay. Now, if I stop loading at this point, the curve will go back along this dotted line, which means that there after loading and unloading, there is a permanent strain of 0.002 in the material. Okay. Now you could select another. You could now every material will have its own. We could use different values of these residual strain for different materials. Also, we could use different values for the same material for different applications. Like if it's an extremely important application wherein you do not want to take any risk, perhaps you could increase it further. You would increase 0.002 to 0.003 so that you make sure that the steel has yielded when failure occurs. Or if it's or you could also use a value of 0.001 and so on. We don't want to get into that. But what in a nutshell, what it means is we define the yield stress here as a stress which is equal to 0.87 Fy, such that this amount of stress is just sufficient to produce a residual strain of 0.002. Meaning that if I load the material up to this point and then I start unloading it, it will not go around this path, but then it will go around this path, and then when you completely release the stress, there'll be a residual strain of 0.002. So this is just to make sure that the material behaves in a ductile manner at failure. Okay. If it is not ductile, if it's still in the elastic region, uh, we might get a brittle behavior. So just to make sure that the steel behaves in a ductile manner, we define our yield point conservatively. Okay. Uh,
So the
yeah.
offset that we take, that is just equivalent to 0.002 strain that occurs in the
Yes.
member, right?
Yes. And this 0.002 is a value. It is a strain value at which the member will not undergo any significant structural damage. Okay. So higher the value we target, higher is the structural damage. It's obvious, like larger the residual strain, larger is the structural damage that we can expect. So 0.002 is a value after a lot of experiments, after a lot of theories, that it is a value for reinforcing steel or for reinforced concrete, that if there's a residual strain of 0.002, there is not going to be any significant structural damage, and therefore the value is 0.002. Okay, any questions? Ishan, did you have an add-on question to that?
No.
Okay, so now, now if you note, when we uh, when we get the design curve for reinforcing steel, we just divide the inelastic portion of the curve. Like even here you see we have divided only inelastic portion of the curve. Okay, even here the same. But if you look at concrete, we divide the entire curve. Right from the origin, we start dividing it with the partial safety factor to get the design curve. So this nainsafi with concrete is because, as you've seen for steel, irrespective of the grade of steel, in the linear elastic portion, the curve remains the same. And therefore, there is quite a lot of certainty as regards to the behavior of steel when it is in the linear elastic region. And therefore, there is no reason for us to divide it with any partial safety factor. Now, when we look at the stress strain curve for different grades of steel, there are different grades of concrete. For example, if you're looking at an M20 curve, that curve might look something like this. Okay, if you look at an M40 curve, that curve might look something like this. 60 curve, that might look something like this. Okay, so right from the origin, the stress strain curve for concrete is dependent on what the grade of concrete is. It is not like steel, wherein, irrespective of what the grade is, the curve still remains the same in the linear elastic portion. So because of this, see, now this particular thing is a measure of modulus of elasticity. And therefore, we have the same modulus of elasticity of steel irrespective of what the grade is. Now, for concrete, E is a function of FCK. Okay, and therefore we sort of have a different value of modulus of elasticity for different grades of concrete. Okay, and because of this variability in the behavior, because of the grade of concrete, we sort of apply the partial safety factor. For example, if you want to come up with a design curve for M20 concrete, you'll divide it right from the origin. So this is our design curve, and this is our characteristic curve. Okay, so the point is that this is these are the basics of concrete and basics of steel. Uh, just to point out that nobody is going to ask this in your exam, but if you have a solid understanding of this, then whatever we do further, whatever we do in flexure, in shear, in compression, etc., it's very easy to visualize it. It is very easy to visualize as to when the material fails under different loading conditions and how we treat it. Okay, so any questions here? Okay, so we'll move on to our next topic. Okay, so the name of the next topic is behavior and design of members in flexure. So what we are going to do uh, from this point is we are going to learn about different structural elements individually, meaning that we are going to learn about beams, slabs, columns, and footings. Okay, so we are dealing at an element level right now. An advanced level would be when you look at all of them together and how all of them together come together. Oh, sorry, how all of them come together to form a structure and how the structure behaves under different loading conditions. So our scope is to look at to look at various structural elements individually. Okay, So, any idea what this flexure is? Okay, I'm just asking, what is flex? I don't want a definition per se. I'm just asking, is this what is flexure? Not a definition, just the meaning of the word. What is flexure?
Twisting.
Bending.
Yeah, I so it's like after I got the first answer, I sort of got a new perception towards this image that you see on the screen. So it seems like the building is twisting, and therefore flexure might have been twisting. Perhaps I should use a different image. What flexure means is bending, simple bending that we have learned since our junior KG. Theory of structures 1, 2, 3, 4, 5. Bending comes everywhere. Okay. So the next question is, which members experience a significant amount of bending or significant amount of flexion? B. Yeah. Any other member except beams?
Slab.
Yes. Any other members?
Whatever members that are horizontal, as in they take load perpendicular to their axis.
Okay. Yes, that's actually a very good definition of defining a member that will undergo flexion. So can columns or structural walls experience flexure?
I think columns would experience buckling before texture.
So we got a very good definition from someone that all the members that are horizontal, that sort of, and that are transversely loaded or that are loaded vertically will undergo flexure. So under the category of this definition, we'll have beams and slabs, which already have been answered. So the question is, what about the vertical members? Would columns or structural walls experience flexure? And yeah, definitely buckling is a design criteria, and buckling is a different phenomenon right now. So we'll get to what buckling is and how we deal with it. But as of now, we're talking about bending. Okay, we have looked at least in terms of the simplest loading conditions in column, we have looked at it multiple times. Remember the example of edge columns, or do you remember the example of corner columns?
Yes.
So any column, uh, or let me put it in a very generic way. If the column or the wall has lateral load, okay, say if a wall is a retaining wall or a basement wall, on a basement wall, there is going to be a soil fill on one side and there's going to be nothing on other side, which means that it is behaving just like a cantilever beam that is vertical. Okay, in that case, that particular wall is being subjected to flexure. Okay, and any structural wall in a system that is being designed for either earthquake or wind will experience flexure. Similarly, if your column is a part of the lateral load resisting system, meaning that if a column and beam together come to form a moment frame such that the frame resists earthquake and wind, then your column is expected to experience flexure. Okay, so the bottom line is general in very normal buildings for gravity loading, beams and slabs are the members which are going to primarily experience flexure. And if we are designing the building for lateral loads, then we can expect significant amount of flexure in not only beams and slab, but also in columns and structural walls. Okay. So flexure or bending is commonly encountered in beams and slabs which are transversely loaded. And normally, flexure does not occur alone. It normally occurs in combination with shear. And therefore, whenever we loaded beams in different forms and different end conditions, and we were asked to analyze it, we drive not only the bending moment diagram but also the shear force diagram. Okay, I'm not talking about this course in your junior KG. Okay, theory of structures 1, 2, whatever. So you must have always looked at shear force diagram along with bending moment diagram. Okay, that's because flexure does not occur alone; it occurs in combination with shear. And we sort of design a beam for flexure, and then we check it for shear, and if required, we design it for shear. Sometimes it also occurs with axial compression, axial tension, and torsion. Okay. Now, concrete is a composite material. So before we develop a theory of bending for material that is homogeneous and composite, we it is advisable to look at the basic theory of bending that is defined for a homogeneous material. Okay, so this is something that I'm sure you've learned before, but before getting into before getting into a composite and a heterogeneous material, if we understand the theory for a homogeneous material, then it is very simple to relate it to concrete. Okay, so every theory is based on certain assumptions. The fundamental assumption when it comes to flexure is something that first I'd like to explain with a picture here, and then we'll get into the actual theory. Okay, so if I take this homogeneous material and if I just draw a grid here, and if I place it on simple supports, and if I load it, now I see that the member has undergone bending or flexure. Okay, the black line that you see that is drawn exactly at the center of this, because since this is a homogeneous material, you can expect that this line will behave as a neutral axis, meaning that this line will not undergo any strain after loading, meaning that the length of the straight line that you see here is exactly equal to the length of this curved line that you see. Okay, and this particular line or this particular axis is called as neutral axis. It is called neutral because it neither experiences tensile strength, it nor it does it experience compressive strength. Okay, so what type of stress do you expect in the material that is above the neutral axis for this loading condition? Anybody?
Compression.
Compressive stress, right? It is quite obvious because what is happening now is whatever is above the neutral axis is getting compressed. You see that the distance between these lines has reduced, meaning that the material above the neutral axis is being compressed, and the material that is below the neutral axis is experiencing tensile stresses. You see that the distance between these two lines now has increased, meaning that the length has increased, meaning that it has elongated, meaning that it has undergone, it is experiencing tensile stresses. Okay, so what this assumption says is that if I draw these vertical lines in an unloaded condition, and if I load it in its deflected shape, these lines would still be vertical. The assumption is very simple. This straight line that I see here is going to be a straight line here also, even after it has bent. It is not going to be in a distorted line. It is going to be a straight line. Okay, very simple assumption, but very profound implications. Now, again, with the help of this, let us try to understand what this assumption means. Okay, say if the distance between these two lines is x, in an unloaded condition. You load it. Now the distance between these two lines at the top is x minus 1. So what this assumption implies is that the distance between the two lines at the bottom is going to be x plus 1. What it means is that the tensile strain at the top is exactly equal to the compressive strain at the bottom. So the reduction in the distance between these two lines is equal to the increase in the distance between these two lines. What it means is that the strain at points that are equidistant from the neutral axis are the same. The only thing is one is a compressive strain, the other one is a tensile strain. But the strains are same, but the numbers are same. So if I take it, if I take this point say at a distance y from the neutral axis, if I get a strain of say 0.0015, if I go y above the neutral axis, you're going to get the same amount of strain, that is 0.0015. The nature is going to be compressive, but the value of the strain remains same. So this implies that a normal cross section that is plane before bending. Okay, now we are looking at this in terms of 2D. Okay, but actually it's a 3D member, and when I say a line, this line represents the entire cross section at that particular point. Okay, you understand what cross section is like. If I just cut it here, whatever section I'll get, that's the cross section. So a normal cross section that is plane before bending remains plane after bending right up to collapse. The way we started understanding it is a line that is straight, a straight line that is drawn on an unloaded member is going to remain straight even when the member bends, which implies that the cross section that was initially plane before bending remains plane after bending right up to the collapse. What it means is that the distribution of normal strain across the beam cross section is linear. Okay, so if I draw the strain variation, say this is the cross section that we are looking at. If I draw the strain variation, this is going to be the neutral axis. Here the strain is going to be 0. Okay, here the strain is going to be maximum. We'll have the same value here but opposite in nature, and this is going to be the strain variation. So 0 at the neutral axis, and as we go away from the neutral axis, the value of strain is going to increase, and here we'll have maximum strain. We'll have an equivalent value here but opposite in nature. So that gives us the variation of strain in the cross section. So this is the fundamental assumption in the theory of bending. Okay. Uh, any questions here? A question can be, or you, a simple suggestion from your end or input from your end is that you did not understand this. Okay, so this is something that you've learned before. This is just a perhaps just a different way of explaining it. Okay, any feedback at this point would be helpful. Have you understood it? Have you not understood it?
Can you re-explain the second point?
Uh, you mean the distribution of normal strains?
Yeah.
Okay. So what it means is, so the strain at the topmost fiber is going to be the same as the strain at the bottommost fiber with an opposite nature. Okay. What it means is that if I go any distance, say a distance y above the neutral axis, so let's say I'm looking at this particular elevation, the strain here is going to be the same as the strain here below the neutral axis, but with an opposite nature. If this is compressive, this is going to be tensile, and vice versa. Means that the strain is linearly varying. Okay, so if I have to draw a plot, okay, so the strain here is equal to the strain here, the strain here is equal to the strain here, here, here. If I join all these points, what I get is a linear variation of strain along the cross section.
Yeah, got it.
Okay. Uh, any more questions? Please go on. See, okay, so I assume that you guys have understood this.
Even the first point actually, can you just repeat
Sorry.
starting? The first point as well actually, can you just repeat once?
Okay. So if I just take a member, if I draw a grid such that I've drawn a line, this is a homogeneous member, this is a homogeneous material. I've drawn a line exactly at the center of this, and then I've drawn some grid lines here just to see how the member behaves when it is loaded in flexion. What I observe is that the length of this line remains the same after it is loaded, meaning that none of the points along this line are experiencing any strain. So I can say that there is no strain, or there is zero strain along this line or along this axis, and I call it as a neutral axis. Okay. Then what I do is I measure the distance between these two lines. So I already know what the distance was. I measure the distance between these two lines after loading, and then at the top and then at the bottom. And then what I observe is that the reduction in the distance at the top is equal to the increase in the distance at the bottom. So what is strain? Strain is nothing but change in dimension upon original dimension. Original dimension is the same. So the change in length at the top is equal to change in length at the bottom between these two lines. What it means is that the strain at the top is equal to the strain at the bottom. The only difference is at the top you have compressive strain, at the bottom you have tensile strain. Okay, so I may do it at various points. I may just do the same thing, and what I'll get is that the strain at a particular distance from the neutral axis is exactly the same as the strain below the neutral axis at the same distance. Okay, so the amount of in case of the example that we are looking at, the increase in dimension along this line is going to be the same as the decrease in dimension along this line along the length. Okay, so the strain at these particular levels is the same. So if I just draw a plot of the strains at various locations along the depth of the section, I will get a linear variation in the strain, meaning that the strain is zero here. The strain has a maximum value in compression for our example, and then it has a maximum value in tension here. Okay, this is what the fundamental assumption of bending means. Is it still unclear?
Yeah, got it.
Uh, I understood what you were explaining, but then I am not getting the wording of the like a cross section plane before bending remains a plane after bending. What does that mean?
What it means is, so the way we understood this example is in terms of these lines. Okay, we have understood this example in 2D, but an actual member is going to be 3D. So when I draw a line here, what it means in an actual member is a cross section. Okay, so a cross section so this is a line. Okay, this is a line. After loading, it still remains a line. It is not distorted. Meaning that if I look at it in terms of 3D, So this is a plane section here. So even after bending, this section remains plane. The section does not distort, meaning that if this is our specimen, and please assume that these lines are straight. After I load it, you so if this line is straight initially, it is going to be straight later on also. You will not see the line going something like this, or you will not see the line going something like this. So if I look at it in terms of 3D, so this particular cross section, which was say plane before bending, it remains plane after bending. Okay, this cross section has not distorted. Say it has not gone like this. What this would imply is that the tensile strain is higher than the compressive strain. Okay, if it had gone the other way, that if it would have uh, the other case would be that the compressive strain is higher than the tensile strain. In that case, you would expect a distortion in this section. Okay, this line, just assume that this line means a cross section. So if you look at it from this side, it will give you a cross section. This is before bending, this is after bending. It was plane before bending and it remains plane after bending, meaning it does not distort. It does not distort like this.
Yeah, understood.
Okay. Any more questions? Okay. So the next assumption is pertaining to the failure criteria, meaning that when do we say that the member has failed? There has to be a certain criteria, right? We cannot say the member has failed after it has fallen. Like it's obvious that it has failed then. But when does it structurally fail? Or when is it that we have attained a ultimate limit state of collapse? Or when is it that the member and hence the member and perhaps the structure is no more usable? Okay, definitely we do not want to wait until the structure falls and then we can say that, oh, now it is no more usable. That would be stupid, right? Before it falls, we sort of want to know that, okay, now this is not usable, it has to be vacated. Okay, so we need a failure point before the collapse, before the actual collapse occurs. And after a lot of research and after a lot of experiments, it has been agreed that we can say that a member fails in flexure when it reaches a strain value of 0.0035. Okay, see, all you've got to do is listen to this lecture carefully. Everything that we are going to do here onwards, all the numericals are based on these assumptions. It's very simple. The only effort that that you have to put is listen carefully. Okay, so it is an agreed value of strain, which is 0.0035. If a strain value reaches this point, we can see that, okay, the beam has failed now. Okay, we don't have to wait until it collapses. It is structurally not usable anymore. Okay, so put it in words. The ultimate state of collapse or the ultimate limit state of collapse is said to have reached in flexure when the maximum compressive strain in the concrete in the outermost fiber reaches the ultimate crushing strain, which is 0.0035. Okay, the way it is denoted is epsilon cu. Epsilon stands for strain, C for concrete, and U for ultimate. What, in general, ultimate means that no, this is an ultimatum. This is final. So epsilon Cu denotes strain in concrete at ultimate limit state, which is 0.0035. Simple. When that strain reaches, we can say that the time is up. So what about steel? So there's another assumption that uh, we consider while designing the member. So the strain in the tension reinforcement at the ultimate limit state shall not be less than epsilon st star, defined as 0.002 plus 0.87 Fi upon Es. We've looked at this particular term some time back when we defined the yield strength for HOISD bar or high strength bars. Okay, now there's a difference between these two assumptions. Assumption number two says that the member fails in flexure when this value is reached. The third assumption says that when failure is reached, we have to make sure that the strain in steel is greater than this value. Okay, so we are defining at failure, we are defining an upper limit for concrete and we are defining a lower limit for steel. We are saying that the maximum, the maximum, okay, let me put it this way. The strain in concrete can have a maximum value of 0.0035. But at the same time, when the failure occurs, the minimum strain in steel should be 0.002 plus 0.87 Fi upon Es. So that is the difference between these two assumptions. And what this assumption implies is that when failure occurs, if we stick to this assumption, or if we design it in such a way that the minimum failure strain is epsilon st, it will make sure that at failure, our steel bars would have yielded, meaning that now they can undergo a lot of deformation before the member actually collapses. So this assumption imparts ductility to the member.
Can you repeat once more?
Okay. So the failure criteria that we have set for a flexural member is that the maximum compressive strain, if it reaches the value of 0.0035, the member has failed in flexure. When it fails, the minimum strain in steel should be 0.002 plus 0.87 Fi upon Es. The reason for this minimum strain is we have defined this strain as a yield strength, meaning that at this value of strain, steel yields. Okay, so if at failure the steel has yielded, meaning that the steel can undergo a lot of deformation at the same value of stress. If it is undergoing a lot of deformation, meaning that it will undergo a lot of deflection before actually collapsing. And why is this important? This is important because it gives us ample warning before the actual collapse occurs. If a beam, say the strain is reached 0.0035 and fatak it collapses, then basically we did not have any chance to get out of the building. There was no warning. It is a brittle failure. Okay. Taking one step back, if at the ultimate limit state the steel is still in the elastic region, it is not going to undergo a lot of deformation because it is still elastic. Okay. It undergoes a lot of deformation when it is in its inelastic and plastic region. So at the same value of stress, it can undergo a lot of deformation. We have seen it in the curve of in the stress strain curve for mild steel in the previous semester, wherein the breaking strain was about 100 times the yield strain. So it can undergo a lot of deformation in its inelastic state before actually collapsing.
Bhargav,
Yeah.
but if the strain is in the linear region, then that's better only, right? For the like if the reinforce if for steel, if E is lesser than EST,
Yes.
then the deformation won't occur, right? So that means that
So
we
we
know that the
want
deformation
okay.
may occur later.
Okay. So we are talking about limit state of collapse. Okay. And if you remember, we worry about deflections only under service conditions. We do not worry about deflections when the member is about to collapse. Okay. Now, when it is about to collapse, we want it to deflect a lot because a larger deflection is giving us a warning that the member is about to collapse and this is the time to vacate the building. Imagine that if the collapse occurs with negligible deflection, you will never know that this building was about to collapse. Okay, so you want the deflections to be minimum under service conditions. You don't want to see any deflections, any sagging in slabs or beams in service conditions. But when it is about to fail, you don't give a damn about deflections then because it is about to fail. And at this point, you want the beam to behave in a ductile way. You want the beam to undergo as much deflection as possible before actually collapsing. So that deflection is a warning that the beam is going to collapse.
Okay, so if E is lesser than EST, then these deflections won't occur.
Yes, because in that case, it is still elastic. In an elastic state, it does not undergo a lot of deflection. And therefore, the beam will not deflect a lot. There will be no warning. The failure would be sudden. So this strain is just to make sure that the behavior of steel is elastic. Okay. Now, one question that we might ask is that this is okay for high strength bars, but for mild steel bars, when we have a fixed yield limit, say 0.87 Fi by ES, why the hell are we using this equation? Okay. Now, this is just to keep things simple. We don't want to define a different strain limit in steel for different grades of steel. Okay. So this is just a conservative number. If it is yielded at 0.87 Fi by ES, definitely it is going to be still yielded at 0.002 plus 0.87 Fi by ES. So that's basically a conservative assumption for mild steel. But this assumption or this number remains the same irrespective of what is the grade of the steel. And this is the number 0.0035, which is the ultimate crushing strain in concrete, irrespective of what the grade of concrete is.
Um, then why do we add that 0.002 again here?
Do you mean for mild steel?
Um, no, for the this equation, EST is equal to
Okay. So when we
I
talk
mean, what
about,
is epsilon EST? Then it should be different, right? Because we are adding that value for high tension steel, which doesn't have that well-defined yield point, right?
yes,
So then, how can it be for any grade of steel? That's what I'm asking.
Okay, so let me put your question in a different way and you just tell me if it is correct. You're saying that this 0.002 plus 8.87 Fi by ES is okay for high strength steel, and we understand because we have defined this as our yield strength.
Yes.
Okay, but why is it for the other grade? So why is this equation still valid for say mild steel? Is
Yes.
that your question?
Yes. Yes.
The answer to this question is yes. For mild steel, you can use an epsilon st star value of 0.87 Fi by ES. That's fine. That is when the mild steel is going to start yielding. And if you're using mild steel, even if your strain value is 0.87 Fi by ES, that's fine. The yielding is already started and you're going to get a ductile behavior. Okay. So the purpose of the code is to simplify things and to make it as less parameter dependent as possible. So what we conservatively, okay, when we are being conservative, it means we're being safe. What we can safely assume is that we can assume the same value of epsilon st star for mild steel as well. What this implies is that we put steel in such a way that at failure, the minimum strain will be 0.002 plus 0.87 Fi by ES. Now, mild steel yields at 0.87 Fi by ES, so definitely it is going to be still yielded at 0.002 plus 0.87 Fi by ES. So the objective is achieved. The objective is that at failure, steel should have yielded. Now at this value, the high strength bars are going to be yielded, okay, because we have defined this as the starting point for the yield of HYSD bars. But for mild steel, yes, this is a slightly conservative number. We have it starts yielding at 0.75 by ES itself. But even at this number, that is 0.002 plus 0.875 by ES, mild steel is still going to be yielded. So this number is little conservative for mild steel, but it is okay for high strength steels.
Okay.
And
Bhargav, but there should, sorry.
yeah, please go on.
I was just saying that there should be an upper limit also, right, for steel because there's only so much it can deflect or like stay ductile.
Yes. So that's a very good point. That if we have a maximum limit for concrete, why the hell do we not have a maximum limit of steel? Okay. And the reason is steel is an extremely ductile material. The member will fail even before steel reaches somewhere around its maximum strain.
Hmm, I didn't get it.
Okay. So steel is an extremely ductile material. Okay. The member that you're using is a composite. It's a reinforced concrete member. Okay. So the amount of strain that steel can undergo is very large as compared to the amount of strain that the member can undergo.
Okay, so it'll fail before that
Meaning
only.
that the member will collapse. It will collapse. It will not fail. It will collapse before even you are near to the maximum strain that is possible in steel. To put it in simple numbers, okay, numbers just for your understanding, okay, these are not real numbers. If the maximum strain that steel can take is 100, okay, we say that the beam fails when the maximum strain in concrete when the maximum strain in concrete is 5. Okay, so 5, the the member is no more, the member has started failing in flexure at 5, at a value of 5. You say that when the strain in concrete is 5, the strain in steel should be 25. So now we have a situation wherein the strain in concrete is 5, the strain in steel is 25. You start loading it further, steel can take up to 100, but at 50 itself, the entire member will collapse. So there is no point in defining an upper limit for steel because the member is not going to deflect that much in any way, it will collapse. Because see, it is reinforced concrete. It's a composite material. It's not we are putting steel in concrete. We are not putting concrete in steel. Do you understand the difference? The behavior is going to be governed by concrete and it is going to be helped in the way we want by steel. So ultimately, even though you are putting steel, but it is not going to deflect up to the upper limit of steel. It will fail before that. It will crush before that.
All right.
Okay.
Understood. Thank you.
Okay. Any more questions? Okay. Moving on. The next assumption is concrete under tension is ignored. Tension is assumed to be carried entirely by reinforcement. What this assumption means is that for our design, we completely ignore the presence of concrete below neutral axis. So all the tensile stresses and the resulting forces occur only in reinforcement. All the tensile stresses are taken up by the reinforcement and none by the concrete. Meaning that if so if this is my cross section wherein I have put reinforcing steel at the bottom, so simply supported beam, what I will consider while designing it, when I say design, I mean fixing its dimensions, fixing the amount of reinforcement, and so on. That so say if this is the neutral axis. So what I'm assuming, the way I'm looking at this section while designing it, is that the section is something like this, and there's concrete only in this region. There's no concrete below this. Why do I make this assumption, by the way? Why am I completely ignoring concrete in this region?
For keeping the margin,
Neha, would you like to answer this question?
The steel bars are taking up the tensile component completely, and the concrete is like the above the neutral axis. The compressive stresses are taken by concrete completely.
Mm-hmm. That's fine. But why do we make this assumption that concrete does not take any tension?
Uh, because the
See,
uh,
Neha, you've already answered this question at the start of the lecture. So I'm just asking you to repeat your answer. Okay, never mind. Yeah, someone was answering something.
because concrete is bad in tensile stresses, so it's assumed to it won't be that much. So it's assumed that the steel will take it all.
Uh, okay, did you mean to say this? That the tensile strength of concrete is negligible. Okay, let me put it this way. The tensile strength of concrete is much lesser than its compressive strength, which is 1/10.
Yeah.
But in addition to that, the tensile strength of concrete is negligible as compared to the tensile strength of steel. Okay, again, to put it in numbers, if the tensile strength of if we have M40 concrete, the approximate tensile strength is 4 megapascals. If you're using Fe415 steel, the tensile strength of steel is 415 megapascals. So you have 415 megapascal guy to defend your tension. Why do you need that 4 megapascal guy for? Okay, yes, it is going to take some amount of tensile stresses, but like you have uh, you have steel that can take 415 megapascals. So 4 megapascals is ignore it. It's just going to complicate our calculations if we consider it. So let us just completely ignore it. Let's assume that everything in compression is taken by concrete, everything in tension is taken by steel. Okay, is this what you meant to answer?
Yeah.
Yeah, perfect. So is it clear why we ignore concrete in tension? Okay, I take it as a yes. Okay, the next is a should we take a small break, couple of minutes, or shall we continue with just 20 more minutes?
We can continue.
Okay. Uh, I just hope that a majority of you guys are awake at this point of time to answer this question. Okay, never mind. So the distribution of compressive strain in concrete across the section is defined by an ideal stress strain curve of concrete. Forget this wording. What this means is, if I take this cross section, let me take the same cross section. Now, what I know is the variation of steel. The variation of this is the strain variation. I know this from the theory of bending, that the strain variation is going to be linear across the section. Now, we have seen the stress strain curve for concrete. So whenever the strain increases linearly, the stress increases in a parabolic manner. Okay, so if I draw the same thing here, what it means is, if this is my strain variation, the stress variation will look something like this. So it's a parabola rectangle. To just recall what this parabola rectangle is, so this is a parabola rectangle. So it's parabola until the value of 0.002, and then it's a rectangle after 0.00, from 0.002 to 0.0035. So if I just draw this line here, which indicates strain value of 0.002, so this is 0.002. This strain value is 0.0035. Similarly, you'll have a maximum stress here. Perhaps I'll not. Okay, maybe I'll write the values. So this value, this is our design curve. Okay, you look at this value. This is 0.45 FCK. So the value that we'll have here is 0.45 FCK. And yeah, we'll have the same value here because the variation is linear. 0.45 FCK here, 0.45 FCK here, the same value. Okay, so if this is the strain variation, this is the stress variation. Parabola and a rectangle. That is what this assumption means. And the last assumption is that if you want to calculate this, the stress in steel, just look at the stress strain curve and you know the value of strain, calculate the value of stress from the value of strain using the stress strain graph. That's it. Yeah. A more important assumption: perfect bond exists between steel and concrete right up to the collapse, because only if there is bond, only then there is going to be a transfer of strains. If there's no bond, there is, like, concrete would be left alone to take tension. It will not be able to transfer the tensile stresses to steel. So it will be like using plain concrete if there's no bond. So there has to be a bond. There has to be a perfect bond between steel and concrete, and we take care of this in detailing, which you're not learning in this course. But it's not just an assumption, but also in practice, we detail in such a way that there's always a good bond between concrete and steel. So this was the basic theory of flexure and reinforced concrete. Okay, so a very uh, so a way of looking at it is it's it's not a very difficult relation between reinforced concrete and steel. Now, to all Tarak Mehta fans, it is just like the relation between Jethalal and Tarak Mehta. So whenever Jethalal is in tension, the first thing he does is he goes to Tarak Mehta. It's just like that. Whenever concrete is in tension, it cannot take tension. It needs a friend like Tarak Mehta. It just goes to steel, and then steel takes the tension. And whenever there's a problem, the role of whenever Tarak Mehta steps in, the role of Jethalal is practically irrelevant, and therefore we just ignore that. Okay, whenever we have a problem, we have steel as a Tarak Mehta, and we do not get into what Jethalal does, meaning that we do not get into what concrete does whenever there's tension. Okay, but to make sure that these behave together, they have to be good friends first. So there has to be a bond between them to sort of get the sort of behavior that we are expecting them when failure occurs, as and when failure occurs. Okay, any questions?
Yeah. Could you elaborate like on how the forces are really transferred within? So I mean, I guess it's a fundamental question about the way that steel and concrete bond, but
Yeah,
we assume them to sort of act as one material, right? Like last you had spoken about how they form like a perfect bond and they act as one material and they have the properties of tensile stress as well as compressive stress, but
yes,
strength. But how does that really work? I mean, in practice, so like if you, I mean, like just now you spoke about how you kind of the concrete in the below the neutral axis becomes redundant uh, um, in terms of taking tension. But
yeah.
how does the steel really take that? I mean, I think that the way in which the forces are really transferred, I think I'm a little unclear about how that happens, like in practice.
Okay. What's your name?
Nishanti.
Yeah. So Nishanti, that's a very good question. So when uh, imagine a concrete beam that is in an unloaded state. In such a condition, the entire compressive strain and the entire tensile strain is taken by concrete. Okay.
Right,
Now
yeah.
you start. Now you start loading the beam, like gradually, धीरे धीरे, start loading it. So as you start loading it, okay, ignore the self weight for the moment. As you start loading it, the compressive stresses are going to increase. The compressive strains are going to increase. Sorry, the compressive strains are going to increase. The tensile strains are going to increase. So before concrete reaches its tensile capacity, meaning before concrete reaches, okay, example given for a 40 megapascal compressive strain of concrete. Let us consider that the tensile strength is 4 megapascals. So before the stresses are less than 4 megapascals, everything is controlled by concrete. It takes the compressive stresses, it takes the tensile stresses. The moment the maximum tensile stress reaches 4 megapascals, concrete starts cracking because it cannot take, because see, concrete is a brittle material. Whenever whenever it reaches the ultimate tensile strain or ultimate compressive strain, so in case of ultimate tensile strain, it starts cracking. Okay, please understand the difference between cracking and crushing. Concrete cracks in tension and concrete crushes in compression. So whenever the value of stress increases beyond 4 megapascals, it will start cracking in tension. Okay.
Right, yeah.
Now, when concrete cracks, it transfers its strain to steel. Why? Because when it is cracking, it is sort of deflecting and it is forcing steel to deflect also. Thereby, it is transferring its own strain to steel. So, in the passive state, meaning that when the stress in the section is less than the ultimate tensile strength of concrete, it's in passive condition wherein reinforcement is not actively participating. Only when problem occurs, only when there is cracking, concrete transfers its strain to steel by cracking. Okay, as you load it further, now you start loading it more, the strains are going to increase, meaning the stresses are going to increase. So initially it was only one crack, one small chotu hairline crack. Now the extent of that crack would increase and the number of cracks would also increase as you increase, as you load it further. So now the steel is getting strained from more and more concrete. More and more cracks are transferring their strain from concrete to steel. Okay, and now steel is moving from a passive condition wherein it was not taking any stress to an active condition. Okay, and this transfer of strain is occurring because there is a bond between concrete and steel. This bond is because steel has cement. Cement is a cementitious material, meaning that it has a property to adhere to something. Okay, it's like a glue that hold all the constituents together. Now, if you are putting steel in that glue, sorry, it is going to stick to that. Okay,
Right,
and
yeah.
steel also has these corrugations. If you've noticed, reinforcing steel have corrugations which act as a key in which the concrete goes and sits. So it is because of the properties of cement, the properties of concrete, and the properties of steel, the mechanical properties of steel, that there is a bond between these two. And because of this bond, when concrete starts cracking, there is a transfer of strain to steel. And as we load it further and further, the extent of cracking increases further and further, and the participation of steel increases further. So at failure, steel moves on from a passive state wherein it was not at all participating to a state wherein it is the only element that is participating in tension. You can just ignore the entire concrete because it is cracked so much that there is no tensile strength left in concrete below the neutral axis. So we are moving from a perfectly concrete state to concrete only in compression state. In the beginning, concrete takes compression as well as tension. At the end, where the collapse is near, concrete only takes compression and steel takes entire amount of tension.
Okay, so then at like so like 90% of the time then steel is in a passive state in
Yes, under working conditions, the the participation of steel is a function of the cracking of concrete. The cracking of concrete is a function of how much stress you are putting in on the concrete. Okay, So we cannot label it as 90%. It just depends on what it is designed for, what is actually loaded. So if there is a frame that is built and kept at it as it is not being constructed further, then you can expect that steel might not even be participating there for gravity loading. It's all concrete because it is not loaded or it is lightly loaded. It just has to take the self weight of the slab and the self weight of the beam, and then you can expect the stresses to be less than the ultimate tensile strength of concrete, and then you can expect that steel is not even participating. As you start loading it, yeah, perhaps then the steel has come into picture, it has started participating, but how much is something that we cannot say unless we know the entire loading condition of that beam.
Okay, okay, that makes
Okay,
sense.
so what we have learned here is that all your beams are cracked. The beams that you see above your heads, which seems perfect, which by the way is because of the plaster and the paint, internally all the beams are cracked. You see, this is so this we want the beam to behave that way. Like we are designing it in such a way that it cracks. So in reinforced concrete, in flexure, beams, slabs, they so the reinforced so let me put it this way. So the reinforced concrete behavior comes into picture or takes an active state when concrete cracks. So there's a very good possibility that all the beams that you see above your head are actually cracked. And that is not a failure. That is a way we work with reinforced concrete.
Okay, okay, I think I understand now.
Okay.
Thank you.
Yeah. Any more questions?
I had one.
Yeah, please.
It's
Go on.
slab. So in the secondary studio, there is a part of a slab which has been reconcreted from below. So I guess the
Could you
part
please repeat it again?
in second year studio, there's a part of a slab where it's been reconcreted. Like it's
Yeah.
look like uh, same thing in the flat scheme which I lived. It was a old building.
Yeah.
So some parts were like falling and the reinforcement was visible. So again,
Yeah.
so
Yeah.
so like it's not total failure.
Yeah, it's not total
But
failure. And that is because, yeah.
but the which we the thing we were discussing like concrete should hold the reinforcement. So
Yes.
at this point it totally loose. So there's no bracing. The connection between the concrete and steel is totally like
Yes,
gone.
it's gone. It's gone. And that is the reason why it is very important to provide sufficient amount of cover. When it is followed, the possibility of exposing the steel, the possibility of concrete falling off the surface and exposing the steel is minimal. This happens only when there is no adequate cover. Okay, and as he rightly said, even though I can see the reinforcement, but it is not collapsing. The reason is that steel is ductile. Okay, had there been only concrete, the entire slab would have come down. But it is because of the steel. Okay, now one thing is sure: if you load it further, it is going to deflect. If you load it the same way it is, if you do not increase, if you just keep using it the way you are using it before, then there's no problem. Nothing will happen because you're not increasing stress or you're not increasing the loading. The problem will occur when you increase the loading. And if you want to relate it to the previous question and the answer to it, if you load it further, there is no bond between steel and concrete to transfer any stresses. So naturally, concrete is just going to start crushing because it does not have anyone to transfer these stresses to. There's no bond. Concrete is gone.
Okay.
Okay. Any more questions?
So in all these considerations, why don't we take into account the compressive strength of the steel as well? Because for a given weight of the material, I think steel is way more efficient in handling compression as well.
Yes, yes. So that's again a very good point. Uh, right now, we are looking into only simple beams and simple slabs that have concrete to take care of the compression, and we put steel only where there are tensile stresses. Okay. Uh, now, what if I need a large span, but because my architect says I have to limit the depth of the beam to a certain value? What will happen then is that the depth of the beam, if I have to say span 6 meters, and the architect says that the maximum depth I can use is only 400, in that case, for a 400 depth, the concrete that I have above the neutral axis might not be sufficient to take care of all the compressive stresses. In that case, if I do not have the option of increasing the depth, I can use Ishan's suggestion to my benefit. What I can do is I can put steel even in the compressive zone. So now you have steel and concrete in the compressive zone, and both of them are going to act together to increase the capacity, to increase the bending moment capacity of the section. So these kind of beams are called as doubly reinforced beams. Okay, the beams that we are talking about until now are singly reinforced, meaning that they are reinforced only on one side, and particularly on the side where there's tension. The answer to this question was pertaining to doubly reinforced beams, wherein the reinforcement is provided not only on the tension side, but also on the compression side. Okay, so yes, we do take the advantage of steel as and when required in compression. And we are going to study these. We are actually going to get into the calculations, and we are going to analyze singly reinforced beam and perhaps a doubly reinforced beam as well. So yes, we'll take the benefit of steel then. But if you ask why is it not done everywhere, the reason is steel is expensive. You want to put as much steel, as much less steel per square feet as possible in a building. If you put little more concrete, that's fine. But if you put like if you're putting compressive steel everywhere, that is significantly going to shoot up your quantity of steel and hence the cost of your structure. So you have to keep the use of steel as minimal, and that is the reason why we don't put it everywhere. Okay, any more questions? Okay, I think we've spent quite some time only on the assumptions. Perhaps uh, this is the first time we've spent so much time only on the assumptions. Nonetheless, if you've got a good hang of it, I think it was worth it. Uh, Please make sure that you read this in the slides. If required, go to books. Uh, just a few more important points left in this chapter. Just modes of failure. Uh, Nonetheless, it's advisable if you could read the entire presentation before the next lecture, so that you already have some basic to what I say, and it's relatively easy to understand. Anyways, so just like today, we'll have a short revision session, which will be linked to your internal marks the next time, and then we'll carry on with the modes of failures in flexure. Okay, so that's it from my side for today. Thank you very much. If you have any questions, I'm available.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.